Now we will discuss the case when we consider the transformation of random variable in the multivariate random variable, transformation of random variable in this for the multivariate random variable. So we can see that we have completed some of the example for univariate random variables. Now we will discuss multivariate random variable, how. So similar concept it may be used. So let us discuss this univariate case again. So whenever we have some random variable x with some probability density function f of x, this continuous random variable, and we want to find a transformation of random variable y is equal to gx, where g is a function r to r, it is a bijective function. So we give the not only that, it is strictly increasing, strictly monotone. So strictly increasing or decreasing function, strictly increasing or decreasing function from r to r, and it has some inverse. So whenever we consider g r to r, so then it has some inverse or strictly increasing or decreasing, h is equal to g inverse exists. So if you have this condition, so then we can, so whenever x is a continuous density function, continuous random variable with probability density function, then we know that how to find the probability density of y. Probability density of y, f of y can be found by d of hy by d y, absolute values of this, then f of x, h of y. So hy is nothing but, so x y is equal to gx. So x is equal to g inverse of y, it exists we assume, and then this is equal to h of y, h of y. So that's why we sometimes write dx by dx dy, f of x, h y. Now these things whether it is applicable for the case when we consider random variable more than for the multivariate cases. So let us discuss, for simplicity, let us consider bivariate random variable. Let x1 and x2 be a bivariate random variable, and it is also continuous bivariate random variable, we denote by x, with probability density function. Let x be a continuous bivariate random variable, continuous bivariate random variable with the joint probability density function f of x. So this function is known. So in general we are writing f of x. So in a particular example, some of the numerical example, we know that what will be the form of the density function. Let g r2 to r2. So here see that because it is a bivariate random variable, this x is a measurable function from sample space S to R2. So we have to consider, so earlier this composite function it was S, then this was R, and then this function it was a measurable function G from R to R. So here it is S, this is R, and this is R. Earlier we discussed this. Now because it is R2, so we have to consider here, because now this random variable x is S to R2. So some value it is taking here. So then this is the some value s here, and then this is xs, and then this point actually under g it is coming here. So g of xs, this function, so this composite function, so this is nothing but we say y of s, this transformation y. So this will be a vector because y will be a vector because it is a bivariate random variable. This is nothing but g of x. So g also a multivariate function, so we can write g tilde. So g tilde of x, so this is function of g of x1 x2, and this is g1 of x1 x2, g2 of x1 x2. It is a component vector. G1 is the function r2 to r, g2 also another function r2 to r, such that g it is going r2 to r2. So but this function having some properties, we need this like earlier for univariate cases. So we discussed that it has to be strictly increasing, and it has to be interpretable, and also from there only increasing or decreasing, strictly monotone. Here also we will assume that g is such a function that, so g is such a function. So if you consider, since it is a bivariate function, basically this function g, this is R2 to R2. So if you consider any x belongs to R2, so that means x is a vector x1 and x2, and y is equal to, this is a vector in R2, g of x. So we take g1 of x and g2 of x. So this is belongs to R2, satisfying such condition that the inverse of g exists. So this is a vector function and given by, we just denote it, h is equal to g inverse, it is denoted. So basically you can find x is equal to g inverse of y, which is equal to h of y exists. Not only that, here you can remember that for invariant cases we discussed the derivative. So derivative either strictly greater than 0 or strictly less than 0. But here if you consider derivative, because it is a bivariate function, so then we have to consider in case of only one derivative, there are many possible derivatives. So those is considered in the Jacobian. So Jacobian is nothing but this, if you consider this matrix, and determinant of the matrix will denote by Jacobian. Actually it is a matrix actually first, then we will take the determinant. So this is defined by, so d x1 d y1 d x1 d y2. So all the partial derivative d x2 d del y1 del, so actually all will be partial derivative. So we can write, so I just for simplicity we are writing, we may understand that del x1 del y1 del x1 del y2, then del x2 del y1, then del x2 del y2, which is it is a Jacobian. Now if you consider this determinant of the Jacobian, so this is the Jacobian matrix, we say we are just denoting J by this determinant of this Jacobian matrix is either positive or negative for all y belongs to the R2. All the possible values of range of y we can consider, but here just I am writing y belongs to R2. So this range may be subset of R2, but it will be either positive or negative for all values of y. It will not be both the cases, either positive or negative for all y belongs to the R2. So now if this condition satisfied by this G, then we have this theorem. So this theorem says that, so this is the theorem that theorem says that let x be a continuous bivariate random variable with the joint probability density function f of x and g R2 to R2 be a function or measurable function, you can say measurable function with the inverse of inverse H is equal to G inverse, and the determinant of the Jacobian, or we can write the Jacobian of the Jacobian matrix J this is del x1 del y1 del x1 del y2 del x1 x2 del y1 del x2 del y2. So determinant of the Jacobian actually I denoted by J actually. So we can write determinant of the J. So let us write Jacobian is equal to this, each either positive or negative for all y belongs to R2. Then the probability density function of y is given by, so y is the random variable, f of y, this is equal to absolute values of this determinant of this Jacobian, f of x of h of y. So this is the theorem. Now this theorem can be extended to, like it is, I just discussed it for, so I have just discussed it for function of two variables, bivariate random variable cases, but it can be extended to n number of variables. So it is here, it is given. So let x, x1, x2, xn be a continuous multivariate random variable with probability density function fxx. Suppose y is equal to gx exists such that x equal to g inverse. So actually y is a gx is a transformation such that g inverse exists, x equal to g inverse of y, hy exists, and this determinant, this is of this Jacobian matrix, is either positive or negative for all y. Then the joint probability density function of y is given by f of y is equal to absolute values of this Jacobian value, determinant of the Jacobian, into fxy. So basically this theorem can be extended to n random variable. Let x is equal to x1, x2, xn be a multivariate random variable. Actually invariate random variable it is, invariate random variable, with the probability density function of x is fxx. Let R G be a, let G Rn to Rn, here we will consider Rn to Rn be a measurable function such that G inverse is equal to G inverse of y, x is equal to G inverse of y, which is equal to hy exists for all y, and this determinant, and J is equal to determinant of this matrix. This is del x1 del y1 del x1 del y2 del x1 del yn del x2 del y1 del x2 del y2 del x2 del yn del xn del y1 del xn del y2 del xn del yn is either positive or negative for all y. Then the probability density function of y is given by f of y is equal to, absolute values of the, because it is either or positive or negative, we will take the positive value. Density function evaluated at h of y. So here h is the vector function, h of y, hy is given here. So this is the theorem. So let us use this theorem. So we have already proved this theorem for univariate cases. Multivariate cases proof will be little complicated. We will not go, we will discuss this. So we have already discussed for univariate cases. So we will discuss some numerical example for multivariate transformation. Let us consider one example. So just for understanding this concept, let us discuss some very simple example. Let x be a continuous, so bivariate random variable with the probability density function of x is given by, suppose this is the probability density function e to the power of minus, so f of x, x1 plus x2, whenever x1 is greater than 0, less than infinity, x2 is greater than 0, less than infinity, 0 otherwise. Okay. So if this is a density function, so note that we are following this notation several times, we have already used it. Capital X1, X2 for random variable, and small x tilde is x1, small x1, x2, xn. This is a real number, and this is actually a function from S to Rn. So this is the notation we are following. So that's why x tilde, whenever we are writing, this is contain x1 and x2, because it is a bivariate random variable. So this is density function. Consider this, consider the transformation y is equal to gx, where g is transformation R2 to R2 defined by, so y will be a vector defined by y1 is x1 plus x2 and y2 is just x1. So this will be a transformation. We will see that whether these are all satisfying or not. So this is in the transformation for the random variable. For real number case, this transformation will be, well, y1 is equal to small x1 plus x2 and y2 will be small x1. So if you find this inverse, so then directly we are getting x1 is equal to y2 and x2 is equal to y1 minus y2, y1 minus x1, y minus y2. So then this g inverse of x, this is nothing but h of, g inverse of y. So x is equal to, hence which is what we are getting here, which implies x, this is nothing but x1, x2. This is the g inverse of y, that is defined as h of y. This is nothing but x1 we are getting y2, and for x2 it is y1 minus y2. So this is the inverse. Now if we find the Jacobian now for this transformation, consider the transformation this. Now next question is that this is the transformation we have considered. Question is that find the probability density function of y, y1, y2, and also find the marginal probability density function of y1. So this is why basically we are interested to know the probability density function of x1 plus x2. So some of the questions, the transformation, it will not be explicitly given R2 to R2, just we are interested to find the probability density function of x1 plus x2, but in the theorem the transformation we need R2 to R2. So we have to consider a bivariate random variable transformation R2 to R2, and then we can integrate out to y2 from the bivariate distribution. Whenever we are finding bivariate probability density function, we can find the marginal of y1. So here in this example, we will find that. So now this part actually okay. So these are the computation part. We will do it. So now what we found that y1 is, so here we found y1 is x1 plus x2 and y2 is x1. So from here we got the inverse, x is g inverse of y, so that is hy. This is nothing but this, what we found, h of y, we found that this is y2 y1 minus y2. So this is y2 y1 minus y2. So this is the inverse we found. Okay. Now we want to find the Jacobian. So basically the inverse is given by x1 is equal to y2 and x2 is equal to y1 minus y2. So now we want to find the Jacobian. So what will be the Jacobian in this case? Inverse exists here, we can find. So what will be the Jacobian? So Jacobian J is given by definition. This is del x1, del y1, del x1, del y2, del x1, del x2, del y1, del x2, del y2. Now from this function we will find that this Jacobian will be, so this is del x1 del y1 will be 0, del x1 del y2 will be 1, del x2 del y1 will be 1, del x2 del y2 will be minus 1. So from here we are getting it. So from del x1 del, because it is a function of y2 only. So then that can be represented, this is like component vector h1 of y1 y2, and this can be written as h2 of y1 y2, but it is a function of y2 only. So that's why the x1 with respect to y, this is 0. Now this determinant is minus 1, which is less than 0 for y, all values of y. So it is satisfying the condition. Hence the joint probability density function of y is given by absolute values of j, then f of x, h of y. So then absolute values of j, because it is minus 1, so this will be 1, and then we have to find what is f of x. So now f of x here you can see that this is 0 to infinity, 0 to infinity. Now this will be e to the power of x1 plus x2. So it will be e to the power of x1 plus x2 here, x1 plus x2 here, y1, 1 into e to the power of minus y1. But the condition is that this x1 has to be greater than 0, less than, so y2 is nothing but x1, this has to be greater than 0, less than infinity. Not only that, this y1 minus y2, x2 also, this function x2, that means y1 minus y2 also, x2 is greater than 0, less than infinity. So now if we combine, otherwise this value will be 0 for any other value. So because this is the transformation, then you can see that x1 it is 0 to infinity, so y2 has to be 0 to infinity, and x2 also between 0 to infinity, so y1 minus y2 also between 0 to infinity. So from here you can get this simplified form e to the power of minus y1, and then this inequality actually it is given if you add y1 both sides, then so what is y1? This y1 also x1 plus x2. So y1 also, so another relationship also we know, y1 also will be less than 0 to infinity. Y1 cannot be negative. Y1 is x1 plus x2. So from here we can get that this three inequality we can combine. You can see that this is 0 greater than y2, less than y1, less than infinity. So because if you add y to both sides, so then y1 has to be greater than y2, and y2 always already greater than 0, so y2 greater than 0, and also y1 is less than infinity, y1 cannot be beyond value. So that's why this is the combinedly we can write, otherwise this value will be 0 otherwise. So this is the joint probability density function of y. Now question is that how to find the now we found the joint probability density function of y1 y2. Now we are interested to know the joint probability density function of y1 only. So the marginal probability density function of y1, this is equal to x1 plus x2, is given by f of y1 y1. So by definition, because we know the joint probability density function y1 y2, if you integrate y2, so then we will find the marginal probability density function. Now this y1 y2, basically we are this notation is same as f of y1 y2 y1 y2. This is just a simplified notation we used. Now we note that whenever we are integrating, so this is non-zero, this density is non-zero in this condition. So we have to find the range of y2 where it is non-zero. So range of y2, because we are doing integration with respect to y2. So range of y2 here between 0 and y1. So hence this is equal to 0 to y1, and then this is e to the power of this value is will be e to the power, otherwise this value will be 0, e to the power of minus y1 d of y2. Now this is independent of y2, so it is e to the power of minus y1 0 to y1 dy 2. If we do the integration 0 to y1 dy 2, if we do the integration, then this is just limit if you put, this is nothing but y1. So this is y1 e to the power of minus y1. So when it is true, so is given by this, it is true actually, because it is not true for all y1. So y1 has to be because y1 can be this, because all y2 depending of the different values of y2. So y1 actually can be between 0 to infinity, any value. So here that's why we have to write. So if given by if y1 is greater than 0 less than infinity, then only this density function we can write. Otherwise in this case y1 is negative, then this will be 0. So hence finally we find the the marginal probability density function of y1 is given by f of y1 of y1. This is y1 e to the power of minus y1 whenever y1 is greater than 0 less than infinity, and this is 0 otherwise. So this is the density function what we wanted to find. So you have hopefully you have understood this concept, how to use this transformation of random variable for finding the joint probability density function for a transform random variable. So we will do more numerical example to understand it better. So it is a simple example. So it is little more complicated, little more like computation needed. This example if you discuss, if you do, because this joint density function given by this function. So let us, and also transformation you can see that. So let x1 x2 xn be a two-dimensional continuous random variable with the joint probability density function this 4x1 x2 e to the power of minus x1 square plus x2 square. Find the joint probability density function of u is equal to u1 u2 transpose, where u1 is given by this and u2 is given by this. Then find the marginal probability density function of u1. So let us find out that.